dense search can miss the exact passage. ColBERT Reranking keeps token-level matching alive, so the best passage rises after retrieval. After this, you'll understand how to assemble a pipeline that gathers dense search candidates and re-ranks them using passage-level evidence. I'm Professor Pi, teaching AI foundations with simple Python. Dense retrievers are fast and great at finding thematically related documents, but they can surface passages that look relevant at a glance, while missing the exact sentence you actually need. That matters when you want a precise fact or a single supporting quote for a generator. ColBERT Late Interaction is the middle ground. You keep dense speed to narrow the search. Then ColBERT inspects token-level alignments to pick the passage that truly answers the query. At a glance, ColBERT scores candidates by comparing query tokens to passage tokens and keeping the best token-to-token matches. Picture a query asking for a specific date. A dense model might rank a general article high, while the passage that actually contains the date wins after ColBERT scores token overlaps. You pay a bit more compute during re-ranking, but since you re-rank only a short candidate list, latency stays reasonable. We'll build a tiny pipeline that shows the pane, loads ColBERT through a helper, runs the re-rank, inspects rank shifts, and packages the chosen spans for a generator. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. First, we will simulate what a dense retriever often returns, so the problem is obvious. This snippet sketches how the dense hits currently favor a thematic but unhelpful passage. We seed corpus with short passages so you can see exactly what evidence each doc offers. Then stuff hand-assigned scores into dense hits to mimic a plain dense retriever. The dense hits.sort call surfaces the top candidate, which is why print reports doc2 with its high score. That's the starting pane. The dense list contains the right topic, but the highest dense score belongs to a passage that lacks the precise fact you want. And now we can watch how re-ranking changes that order. Now that we have a clear failure case, we load ColBERT so it can score token matches on those candidates. This example loads ColBERT through RAGatouille so we can score our candidate passages later. The RAGPretrainedModel .FromPretrainedCall pulls the default ColBERT v2 weights without forcing you to wrestle the raw model API. We reuse dense hits to build candidate IDs, then map them back to the raw text via candidate texts, so the re-ranker sees the actual passages. The printed document count confirms ColBERT now has 3 textual candidates queued, giving you confidence the setup succeeded. This step keeps model loading and candidate prep separate, so the re-rank step only needs to worry about scoring. With ColBERT available, we ask it to re-rank the dense candidates and inspect what it prefers. This code uses RAGatouille's rerank to let ColBERT overrule the dense baseline. The RAG rerank call feeds the original query, the candidate texts, and their candidate IDs, letting ColBERT compute token-level maxim scores. Passing k equals len candidate IDs keeps every candidate in play. You could lower k to trim latency by skipping tail documents. We grab top_ColBERT from the returned list and print its identifier and score so you can see which passage ColBERT now trusts most. This is the heart of late interaction. Dense retrieval narrows the field, and ColBERT inspects token evidence to reorder that short list more precisely. Next, we measure how much the ground truth passage moved after ColBERT intervened. This snippet checks how far the ground truth passage climbs once ColBERT has a say. We mark target doc as the evidence-rich chunk and compute its dense baseline rank with an enumerate over dense hits, then walk re-ranked to capture the new ColBERT position. The printed shift, such as 2 to 1, validates that late interaction re-ranking surfaced the right evidence. Seeing a concrete rank change matters because it shows ColBERT is promoting documents with the exact tokens the query needs, not just reshuffling noise. Finally, we prepare the top spans, so a generator can use the elevated evidence. This example packages the re-ranked top span into a context string ready for generation. Taking re-ranked 2 keeps only the most relevant passages, though you can widen that slice if your generator needs more coverage. We assemble final context by joining the raw text keyed by document ID, preserving the exact evidence ColBERT elevated. The concluding print lists the chosen IDs alongside character count, so you can sanity check the payload before handing it to a language model. This wrapping step is practical and shows how re-ranking fits into an end-to-end retrieval augmented generation flow. In a production flow, you would swap the tiny toy corpus for your document store and call your dense index instead of the hand-seeded hits. ColBERT then acts as a precision layer that keeps token alignment alive, while still benefiting from a fast approximate search stage. What this gives you is dense recall with token-level precision. Use it when exact passages or facts matter, and a rough thematic match isn't enough. One short caveat: re-ranking costs extra compute, so keep your candidate set small and focused. A useful next step is to experiment with the re-rank window and final slice size. Try increasing the number of candidates you send to RAG.ReRanked and widen re-ranked 2 so the generator sees more evidence. Then measure generation accuracy on a held-out question set. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.